We are constantly surrounded by this magnificent complexity.
Absolutely everywhere we look.
And yet, it really feels like the deepest, most profound answers are hiding in the simplest, most everyday questions. Things like, why is the sky blue?
Or why are planets around?
Exactly. Or why does a snowflake, this tiny, fleeting piece of ice, always choose to have six corners?
Welcome to the deep dive. Today, we are taking a guided journey, really, through the fundamental laws that govern, well, everything. We're diving into the source material from forces of nature.
And our mission here is to use these sources as a kind of a mental altitude gauge. We want to move from the tiniest quantum world, the world of quarks, all the way out to our spinning planet, and then finally to that vast philosophical view from space.
All in pursuit of one central idea.
Yeah.
And that idea is this. When you look at Earth, you see this staggering complication.
Oh, absolutely. 10 million species, hundreds of countries, thousands of religions.
Right, what the sources call a parochial fog. But all of that complexity exists under the government of a remarkably small, elegant, and simple set of fundamental physical laws.
That's the tightrope we're walking today, isn't it? The laws are few and simple, but the things they create us, planets, snow, are infinitely diverse. So we need to figure out where that simplicity ends and where the specific history of an object begins.
Exactly. We're trying to separate the universal rules from the specific details. We're looking for what you could call the profound economy of description in the universe. And to do that, we have to start with the most basic building blocks.
Okay, so let's unpack this economy right away. If I were to take any object, say this desk or a mountain or even myself, and break it down into its smallest, most fundamental parts, what's in the toolkit? How small is it really?
It's astonishingly minimalist. I mean, you can forget the entire periodic table for a moment. All of the stable matter you interact with every day is built from just three essential particles.
Just three.
Just three. The up quark, the down quark, and the electron. That's it. The protons and neutrons in the nucleus of an atom. They're just different combinations of those up and down quarks.
Wow. And these three particles are then governed by a handful of rules, the fundamental forces. I think the source material calls them the famous quartet.
That's right. The quartet includes the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. And of course, we have to give a nod to the Higgs boson, which gives these particles their mass.
So a handful of particles and four rules. The idea that this tiny collection of laws generates everything from a water molecule to a star, it's genuinely humbling.
It is. There's no reason reality had to be this organized or, this frugal in its design.
So let's start with the workhorse, the force responsible for pretty much all of chemistry and life as we know it,
Yeah.
electromagnetism. What's its job description?
Electromagnetism governs every interaction between charged particles. So it binds the negatively charged electrons to the positively charged nucleus to make a stable atom.
Okay, that makes sense.
But then, crucially, it links those atoms together to form molecules. Think about a water molecule, HO. The electromagnetic force handles how the electrons are shared between the oxygen and hydrogen.
And that sharing isn't perfectly even, is it? That's the key.
Exactly, it's uneven. It makes water a polar molecule with slightly positive and negative ends. And that polarity is critical.
Because it lets water molecules stick together through what we call hydrogen bonds. And that stickiness is why water is a liquid at room temperature, which is pretty useful for life.
And as we'll see, it's what dictates the incredible structure of a snowflake. But think about this. If electromagnetism is all about attraction and repulsion, consider the challenge inside the nucleus of, say, an oxygen atom.
Right. An oxygen nucleus has 8 protons, all positively charged. They should be repelling each other with incredible force.
They should be flying apart instantly. So for them to be crammed together, something else must be at play.
Something much, much stronger.
That's where the strong nuclear force comes in. It is by far the strongest of the 4 forces. It's carried by particles called gluons, which, as the name suggests, literally glue the quarks together inside protons and neutrons.
So it's like a cosmic superglue.
But it's a very short-range heavy hitter. It's confined almost entirely to the nucleus. Its influence just drops off to nothing outside the atom.
Okay, so that's the strong one. What about its counterpart, the weak nuclear force? It's also at the nuclear scale, but it does something totally different, right?
Weak force is the great transformer. It mediates processes where one type of particle can actually change into another.
An alchemist.
That's a perfect way to put it. It can flip a down quark into an up quark, which turns a neutron into a proton, or vice versa. This radioactive decay process is what makes the sun shine.
Really? How so?
Well, the very first step in the fusion chain that powers the sun requires two protons to fuse, and in that process, one of them has to turn into a neutron. The weak force is what enables that conversion. Without it, the sun's engine couldn't even start.
So we've got the strong force holding nuclei together, electromagnetism handling all of chemistry, the weak force fueling stars. That just leaves gravity, the one we feel every second, and yet it's the odd one out.
It's the profound outlier. Gravity is, paradoxically, the weakest of the four forces by an almost unimaginable margin.
How weak are we talking?
If you compare the gravitational pull between an electron and a proton to their electromagnetic attraction, gravity is about 40 orders of magnitude weaker. That's a 1 with 40 zeros after it.
Yeah, I can't even picture that number. It explains why a tiny refrigerator magnet can beat the gravitational pull of the entire Earth to hold up a piece of paper.
Exactly. We only notice gravity because planets are so ridiculously massive. And this weakness is probably the single biggest unsolved mystery in fundamental physics.
Why is it so weak?
We don't know. Its strength is set by a measured value, Newton's gravitational constant, g. It's a fundamental property of our universe, but we have no theory that explains why g has the tiny value it does.
Unlike the other three forces, which are sort of mathematically linked in the standard model.
Right. The extreme weakness of gravity is what prevents us from creating a single, unified theory of everything. So physicists have to speculate.
That they were all unified at the very beginning.
At the instant of the Big Bang. The hypothesis is that at something called the Planck temperature, a ridiculously high number, all four forces had the exact same strength. They were one single, unified superforce.
And as the universe expanded and cooled, they froze out at different strengths.
That's the idea. The symmetries broke. The strong force separated first, then the weak and electromagnetic. Gravity seems to have separated earliest and, well, weakest. And that disparity is what dictates the architecture of the cosmos. Gravity shapes the planets, but electromagnetism makes the rocks rigid enough to form mountains. So moving from the forces themselves to the shapes they create, we see these laws imprinted everywhere. And there's no better place to start than the exquisite geometry of the snowflake.
Ah, the classic story of Wilson Snowflake Bentley. He spent his life photographing over 5,000 unique snow crystals.
And he cemented that famous idea. No two are alike.
But every single one of them shares that fundamental six-fold symmetry, the sixness, as Kepler called it. He wondered, why always 6 corners? Why not 5 or 7?
And that sixness is a direct manifestation of the underlying physics. It's a pattern dictated by quantum mechanics, and we can trace it all the way back to the water molecule.
Okay, so we established that electromagnetism gives the H0 molecule its specific shape.
That's right. The quantum rules force the 2 hydrogen atoms to bond to the oxygen at a very specific angle, 104.5 degrees.
And that angle is everything.
It's everything. When water freezes into its most common structure, we just call ice 1-out, that 104.5-degree angle forces the molecules to arrange themselves into a repeating hexagonal lattice. It's the most efficient way for them to pack together. So when you see a 6-sided snowflake, you are literally looking at the primal structure of the universe imposed by quantum rules.
That explains the symmetry, the sixness. But what about the endless individuality that Bentley documented? Where does all that complexity come from?
That comes from history. The long and messy part of the process, as the sources put it. A snowflake's final shape is determined by the constantly changing conditions it experiences as it falls through a cloud.
Right, the journey matters. The sources describe it as a kind of competition between two different effects.
The first is called faceting. If a crystal has any rough edges or bumps, water vapor molecules are more likely to stick in those little hollows, and that tends to smooth the surface out. Faceting pushes the snowflake toward being a simple, flat, hexagonal prism.
Bit boring, then.
A bit boring, yes. But if the air is really humid, rich with water vapor, you get the opposite effect, which is much more dramatic.
Branching instability.
Precisely. In humid air, any little bump that forms on one of the corners sticks out further into the moist air, so it collects water vapor much, much faster than the flat surfaces. This instability causes these beautiful, intricate arms to shoot outwards.
So a snowflake's unique shape is basically a written record of its journey through the cloud. A bit of faceting in a dry layer, then a lot of branching in a wet layer.
And back and forth. The laws ensure symmetry because the conditions around all 6 corners are identical at any given moment. But its history ensures its individuality. It's a beautiful tension.
It really is.
Yeah.
Okay, from frozen water to wax, the other great hexagon in nature, the honeycomb. Why do bees build these perfect hexagons? Is it just pure instinct for efficiency, or is geometry winning again?
Well, this is a wonderful scientific debate. The classical Darwinian explanation is all about efficiency. The hexagon is mathematically the most efficient shape for dividing up a flat plane.
Meaning it uses the least amount of wall, the least amount of wax to enclose the largest possible area.
Correct. And that efficiency matters a ton. Producing wax is incredibly costly for bees. They might have to eat 8 grams of honey just to secrete 1 gram of wax. So natural selection would strongly favor any behavior that saves wax.
And this isn't just a hunch, right? It's been proven mathematically.
It has. Thomas Hales proved the honeycomb conjecture in 1999, confirming the hexagon is the optimal shape. Case closed, you might think. But a more recent theory from 2013 challenged the idea that bees are consciously engineering this.
This is the theory from Carihelu, Zhang, and Wang. They suggest the hexagon just happens spontaneously.
Yes, they observed that bees actually start by building circular cells.
Oh, interesting.
But then, the collective body heat of the bees in the hive raises the temperature of the wax to about 45 degrees Celsius. At that point, the wax softens and becomes pliable.
Ah, and when the wax is soft, physics takes over.
Exactly. The surface tension of the softened wax makes the circular cells pull on each other to minimize their surface area. It's the exact same process you see with soap bubbles in a foam,
And soap bubbles always meet at 120-degree angles.
which forces the shape into a perfect hexagonal grid. So it might not be a genetic blueprint for a hexagon, but rather a blueprint for building with a material that, when heated, automatically finds the most efficient shape. Geometry wins again.
That's incredible. It's a fantastic bridge from the small scale to the astronomical. Because when we look up at stars and planets, we see the same principle at work. A simple law, creating a simple universal shape. The sphere.
Gravity is the grand sculptor here, and it comes back to the simple elegance of Newton's law of universal gravitation. The equation, F equals gmm over r squared, only depends on mass and distance.
Crucially, it has no preferred direction in it. The law is the same whether you're pulling from the top, the bottom, or the side. It has what you call rotational symmetry.
And a symmetrical law will always produce a symmetrical object, given the chance. When a body like a planet gets big enough, its own gravity overwhelms the structural rigidity of the rock it's made of.
A rigidity which, remember, comes from the electromagnetic force.
Right, so gravity pulls equally from all directions, and it just squashes all the matter into the most symmetrical, lowest energy shape possible.
Which is a sphere.
A sphere.
And this gives us a testable prediction, doesn't it? Based on the material, there must be a minimum size for an object to become round.
There is. For a body made of rock, the calculations show that its radius needs to be more than about 600 kilometers before gravity can overcome the rock's rigidity. Below that, it can stay as a lumpy, irregular shape.
So you can look at Mars's little moon Phobos, which is an 11-kilometer-long potato, and you know instantly it fails the test.
But then you look at an icy moon, like Saturn's Mimas. Ice is much easier to deform than rock. So for icy bodies, the minimum radius for becoming a sphere drops to around 400 kilometers. Mimas makes the cut.
So the shape of every object out there is just a function of its mass, its composition, and that unwavering, directionless pull of gravity.
But the perfect sphere isn't ideal. It's rarely achieved in practice because of one key factor: symmetry breaking.
Things spin.
Things spin, and rotation introduces a special direction, an axis of spin, which immediately breaks the perfect symmetry of the gravitational law.
Our own planet is the perfect example.
Earth is not a perfect sphere. It's an oblate spheroid. The centrifugal force from our daily rotation pushes mass outwards at the equator. So the equatorial circumference is a bit bigger than the polar circumference. It bulges at the middle.
And the faster something spins, the more it flattens.
It's a universal principle. It explains why a huge, rapidly rotating system, like a spiral galaxy, flattens out into a thin disk. But a globular star cluster, which has very little overall rotation, stays beautifully spherical. The shape of a thing is its history, written on top of the laws of physics.
Okay, we've seen these laws at every scale. Let's bring it right back home to the things we experience every day, starting with a classic misconception: what causes the seasons?
So many people think it's because our orbit is an ellipse and we get warmer when we're closer to the sun.
Right, it feels intuitive.
It does, but it's completely wrong. And you
Yeah.
can prove it with a calendar. The Earth is actually closest to the sun, a point called perihelion in early January.
Which is the middle of winter for everyone in the northern hemisphere. Meanwhile, it's peak summer in Australia, so that can't be it.
It can't. The real cause is the Earth's 23.5-degree axial tilt. That tilt is the single most important factor for our climate.
So in June, the northern hemisphere is tilted towards the sun. The sunlight is more direct, the days are longer, and we get summer.
And in December, it's tilted away. The same amount of solar energy is spread over a much wider area, the days are short, and we get winter. It's all about the angle of the sunlight.
And just like the shapes of planets, this tilt isn't some fundamental law. It's the result of a specific, violent event in our past.
It is. It goes back to the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized object, which we've named Theia, smashed into the early Earth.
A truly cataclysmic collision?
It was. The impact melted everything, formed the Earth's core, and crucially, knocked our planet onto its side, setting that 23.5-degree tilt. The debris that was thrown out into orbit eventually coalesced to form the Moon.
And the moon isn't just a pretty light in the sky, it's absolutely critical for our long-term climate.
It's a stabilizer. The Moon's gravitational pull acts like a giant gyroscope, preventing our planet's tilt from wobbling wildly over millions of years. Without the Moon, our axis could swing from 0 to, say, 80 degrees.
Which would cause absolutely chaotic climate change. No stability for complex life to evolve over geological time.
Many scientists believe that stability is a key reason we're here at all. We owe a lot to that ancient collision.
Now, that spinning motion of our tilted planet introduces other effects. Because we're rotating, the ground beneath our feet isn't a stable, fixed point. It's what's called a non-inertial reference frame.
This is a tricky but vital concept. An inertial frame is where Newton's laws work perfectly. An object at rest stays at rest. But on a spinning surface, you're constantly accelerating just by moving in a circle.
And because our reference frame is accelerating, we invent these fictitious forces to make the math work out.
Think of being in a car turning a sharp corner. You feel a force pushing you outwards against the door. That force isn't real. It's just your body's inertia trying to go in a straight line while the car turns underneath you.
Okay, that makes sense.
The Earth's rotation creates a similar apparent force called the Coriolis Force.
Named after Gaspard Gustave de Coriolis. How does this fictitious force affect things like the weather?
It deflects any moving object air masses, ocean currents, even a cannonball. In the northern hemisphere, the deflection is always to the right of the direction of motion. In the southern hemisphere, it's to the left.
And this is fundamental for all large-scale weather, like hurricanes.
Absolutely.
Yeah.
When air rushes in toward a low-pressure zone, the Coriolis force deflects it sideways. It can't go straight to the center. That sideways push is what starts the storm spinning.
So in the north, that rightward deflection makes the storm spin anti-clockwise.
And in the south, the leftward deflection makes it spin clockwise. And you can see this is a universal law just by looking at Jupiter. Its great red spot is a gigantic, persistent anti-clockwise storm. The same physics applies everywhere.
And this idea of fictitious forces also helps explain the tides, right?
It does. The moon's gravity obviously causes the tidal bulge on the side of the Earth facing it. But there's also a bulge on the far side.
Which is caused by a fictitious centrifugal force.
Yes, because the Earth and Moon are actually orbiting their shared center of mass, which is a point inside the Earth. As the whole planet orbits that point, it creates an outward centrifugal force. On the far side of the Earth, that centrifugal force is stronger than the Moon's weakened gravity, and it pulls the water up into a second bulge.
It's all connected. The tilt, the spin, the storms, the tides, all consequences of living on a large rotating sphere.
A large spinning blue sphere.
Right. And that brings us to the colors of the pale blue dot, the blue sky and the blue ocean. They seem related, but the physics is totally different. So first up, why is the sky blue?
This is all thanks to a process called Rayleigh scattering. Our atmosphere is mostly tiny nitrogen and oxygen molecules, much smaller than the wavelength of visible light.
And when sunlight hits these molecules, it gets scattered.
It gets scattered. And the crucial part is that the amount of scattering depends very strongly on the light's wavelength. The formula shows it's inversely proportional to the fourth power of the wavelength.
The fourth power. So a small change in wavelength makes a huge difference in scattering.
A huge difference. Blue light has a much shorter wavelength than red light, so it gets scattered more than 3 times as effectively.
So the blue light is essentially ripped out of the sunbeam and sprayed all across the sky. And our eyes see that scattered light coming from all directions as a blue dome.
That's it. And a red sunset is just the flip side of the same coin.
Because the sunlight has to travel through much more atmosphere to reach you.
Exactly. That long path means almost all the highly scatterable blue light is scattered away from your line of sight before it even gets to you. The only light that makes it through directly is the unscattered, long wavelength light, the reds and oranges.
Okay, so that's scattering. But the ocean's blue is a different process entirely. It's absorption.
Right. Water molecules are really, really good at absorbing light, especially red light. The energy from the red photons makes the water molecules vibrate, and it's converted into heat.
The sources say if you take a bright red object just 15 meters underwater, it looks black.
Because there's virtually no red light left to reflect off it. The water has absorbed it all. So as you go deeper, the visible spectrum is stripped away, color by color. The last colors to be absorbed are blue and green, which are then scattered back to our eyes.
So scattering in the sky, absorption in the sea, two different mechanisms creating our planet's signature color. So we've established that the laws of physics are simple, elegant, and they lead to ordered structures. But now we have to face the biggest challenge to that simplicity: life itself, the most complex, ordered thing we know of.
And it seems to fly directly in the face of the universe's most fundamental rule,
The second law of thermodynamics.
the second law. It states that the entropy or disorder of an isolated system will always increase over time. Things fall apart, your coffee gets cold, the universe trends relentlessly towards chaos and heat death.
But life is the polar opposite of that. We are incredibly ordered, low-entropy systems. This feels like a massive contradiction, the old idea of a warm little pond just stewing for millions of years.
It doesn't work. As the source material points out, a gently stewing soup will just break down. It won't spontaneously assemble itself into a complex cell.
Because creating order requires energy. It's an uphill battle against statistics.
Exactly. The second law is really a statistical truth. There are just infinitely more ways for things to be disordered than for them to be ordered.
So how does life cheat the system? How does it win that statistical battle?
The key is that living things are not isolated systems. That's the crucial distinction.
Oh, okay.
Life is able to build up its local order, to lower its internal entropy, but only by exporting a massive amount of compensating disorder, usually as waste heat, into the rest of the universe.
So on balance, the total entropy of the universe still goes up.
It goes up even faster because of us. Life is a mechanism for accelerating entropy production. The best analogy is that life exists in a waterfall. It taps into a powerful external energy gradient.
Okay, a waterfall of energy.
Think about it. A waterfall exists because there's a huge energy difference between the water at the top and the water at the bottom. Life on Earth today taps into the energy gradient between the hot sun and the cold deep space.
Through photosynthesis.
Through photosynthesis.
Okay.
Plants take in low-entropy photons from the sun and use them to build highly ordered structures like sugars and cells. In the process, they release high-entropy waste products like heat and reactive oxygen. So life doesn't defy the second law, it's a manifestation of it.
That's a huge conceptual shift, but that leads to the next problem, the primordial cradle. Before photosynthesis evolved, there was no sun-oxygen gradient to exploit. So what was the original waterfall?
We have to look for a smoking gun, a universal energy mechanism that all life shares, a relic from the last universal common ancestor, or LUCA.
And we find that in how our cells produce energy.
We find it in every living cell on Earth. All life, from bacteria to us, uses a system of proton waterfalls and intricate respiratory chains to make ATP, the universal energy currency.
A proton waterfall.
Yeah, cells pump protons across a membrane to build up an electrochemical gradient, like water behind a dam. Then they let the protons flow back through tiny molecular turbines to generate energy.
That sounds incredibly complex. Too complex to have evolved from scratch.
That's the thinking. The place where life began must have provided those proton gradients for free. The first life just had to learn how to harness them.
And this points us to a very specific location.
It points us to deep-sea hydrothermal alkaline vents, places like the Lost City Field in the Atlantic.
Why those vents specifically?
Because they're not the super hot, acidic black smokers. These are cooler, and they bubble up highly alkaline fluids into the slightly acidic ocean water. That natural difference in pH creates the exact kind of electrochemical proton gradient life needs, right there in the tiny pores of the vent rock.
So the vents provide the energy gradient and the basic chemicals. The rock pores act as the first cell walls.
And it drives simple inorganic chemistry spontaneously up the hill towards complex biochemistry. If this theory is right, we're all carrying a memory of our origin inside us. Our cells are just recreating the conditions of those primordial vents. It's what life has always done.
And if life emerges spontaneously when you have these conditions, it gives us a clear target in the search for life elsewhere.
A very clear target. We look for worlds with liquid water and active geology. And that brings us to one of the most exciting places in the solar system, Saturn's tiny moon, Enceladus.
The Cassini probe found something incredible there.
It flew through these huge plumes of water erupting from the moon's south pole. This confirmed an active, subsurface ocean. But the amazing part was what was in the water,
Not just organic molecules.
but also tiny grains of silica. And those silica nanograins only form when liquid water interacts with rock at temperatures above 90 degrees Celsius.
So that's the smoking gun for active, hot, alkaline hydrothermal vents on the ocean floor of Enceladus right now.
It's the best evidence we could hope for. Enceladus today looks a lot like Earth might have looked 4 billion years ago. If the thermodynamic argument is right, it could be the strongest candidate we have for finding life beyond Earth.
Okay, this journey has taken us from a single bond to the origin of life itself. Now we need to shift focus again to the deepest level of reality, the structure of matter and the structure of space and time.
We're going inside the proton, and then we're going to talk about Einstein.
Let's start with the proton. The source material uses the example of the HER particle accelerator in Germany, basically a giant electron microscope.
That's a good way to think of it. Its purpose was to smash high-energy electrons into protons to see what's inside. And what you see inside a proton is, well, it's quantum chaos.
It's not a neat little package of 3 particles.
Well, not at all. At low energy, low resolution, you do see the electrons scattering off 3 distinct objects, the 2 up quarks and 1 down quark.
The classic picture.
The classic picture. But when they cranked up the energy, increasing the resolving power, that simple picture just dissolved.
What did they see instead?
They saw the structure change dramatically. The 3 quarks seemed to be swimming in a seething sea of other, more transient particles.
And these are the gluons.
These are the gluons, the carriers of the strong force. The electron, at high resolution, was scattering off this fluctuating cloud of gluons being constantly exchanged between the quarks. In fact, about half the momentum of a proton is carried by this gluon sea, not the quarks themselves.
And the beauty of it is that this incredible seething chaos is described perfectly by an elegant mathematical theory.
Quantum chromodynamics, or QCD. Yeah. It's the theory of the strong force, and it predicts all of this complexity with stunning precision. It's a deep, beautiful truth revealed by these immense machines.
Okay, so from the structure of matter to the structure of reality itself, Einstein's relativity, what was the conflict he was trying to solve?
He was trying to reconcile 2 pillars of physics, Newton's laws of motion and Maxwell's new laws of electromagnetism.
And Maxwell's equations had a strange prediction built into them about the speed of light.
A very strange one. They predicted that light is an electromagnetic wave and that it travels at a fixed, constant speed, c. The problem was, the math demanded that everyone, no matter how they were moving, had to measure the exact same speed of light.
Which violates our common sense. If I'm driving my car towards you, I expect to see the light from your headlights coming at me faster than if I were standing still.
Right. It violates simple speed addition. But Einstein took Maxwell's prediction not as a problem, but as a fundamental postulate of the universe. The speed of light, c, is constant for everyone, period.
And to make that true, he had to throw out some very old, very cherished ideas.
He had to sacrifice the concepts of absolute space and absolute time. To keep c constant, space and time themselves have to become fluid and relative.
This is where we get time dilation and distance shrinkage.
Exactly. Moving clocks have to run slow. Moving objects have to appear shorter in their direction of motion. These aren't illusions. They are real physical consequences of the structure of reality.
And they're not just theoretical, right? We have to account for this in everyday technology.
We do. The GPS satellites in orbit are moving very fast, and their clocks run slightly slower than ours because of time dilation. If the system didn't constantly correct for relativity, your GPS would be off by kilometers within a single day.
So this all leads to the unified concept of space-time.
Right. It was Hermann Minkowski who really solidified it. We don't live in 3 dimensions of space plus 1 of time. We live in a single 4-dimensional continuum.
And while you and I might disagree about distances in space or intervals in time between 2 events,
We will always agree on the distance in space-time. There's an equation that combines space and time, with c as the conversion factor, and that value is absolute for all observers.
And see, the speed of light isn't just a speed, it's the universal speed limit.
It is. And by being the speed limit, it protects the most fundamental thing of all, cause and effect.
How does it do that?
It creates what we call the light cone. Any event that can possibly influence you has to be inside your future light cone. For those events, the time ordering is fixed. The cause will always precede the effect, for every observer.
But for events outside the light cone?
For events that are so far away that light hasn't had time to travel between them, they are space-like separated. And for those events, different observers can actually disagree on which one happened first.
But that's okay because they can't influence each other anyway.
Exactly. Causality is safe. But this whole idea of a fixed, unified spacetime leads to a very strange philosophical idea: the block universe.
The idea that the past, present, and future all exist simultaneously.
If reality is just this four-dimensional block of spacetime, and we are just experiencing a slice of it as we move through it, then it suggests a very deterministic universe. The future is already out there, just as the past is.
Which raises all sorts of uncomfortable questions about free will. Our experience is one of a flowing present moment.
But relativity suggests that might just be a persistent illusion. The entire history of the cosmos could be written, start to finish, into the fabric of spacetime. A pretty profound and unsettling idea, all derived from the simple postulate that the speed of light has to be constant. So this whole journey from quarks to spacetime, it has to lead us back here. Back to a change in our own perception, the kind of shift that astronauts talk about when they see the Earth from orbit for the first time.
The source material is filled with these really evocative quotes. Yuri Gagarin seeing that light blue aureole around the planet.
Frank Borman on Apollo 8 saying how all the national differences just blend into one world.
And Mike Collins, who was orbiting the moon alone, looking back at Earth and just thinking, my God, that little thing is so fragile out there. Science gives us that same kind of mental altitude, doesn't it? It lifts us above that parochial fog and lets us see the bigger picture.
And there is no bigger picture than the one provided by the pale blue dot image.
Taken by Voyager 1 in 1990 from 6 billion kilometers away, Earth is just a tenth of a pixel.
A tiny crescent of light suspended in a sunbeam. And Carl Sagan's reflection on that image is, it's just devastatingly beautiful and necessary.
He calls Earth a lonely speck in the great enveloping cosmic dark.
And he says that on that speck is everyone you've ever loved, every hero and coward, every king and peasant, the entire history of our species played out on a mote of dust.
It forces you to confront our cosmic insignificance. If you really accept that our existence is just this contingent lucky accident, you have to jettison all the self-importance.
Exactly. The conclusion is inescapable. We have to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. If there's no grand cosmic purpose for us, then we have to create that meaning right here.
But being small doesn't mean we're without value. Our existence, even if it's contingent, is magnificent. The evolution of life, of intelligence on this planet is an incredible story.
And our intelligence is what brings meaning to this little corner of the universe, at least for a while. And this brings the whole journey full circle.
To the search for other pale blue dots.
Yes. That faint light from our planet carries an encrypted database of our chemistry and geology. And when astronomers look at exoplanets, they're looking for that same encrypted information, the biosignatures.
They're looking for the colors we talked about. The blue of Rayleigh scattering from an atmosphere. The dip in the spectrum that shows water absorption.
And most of all, they're looking for the spectral fingerprint of free oxygen in an atmosphere, which is a massive, screaming sign of photosynthetic life remaking an entire planet.
So, understanding the simple laws that make a snowflake hexagonal, that make our sky blue, that make life a thermodynamic necessity, that is precisely how we search for company in the cosmos.
So to just quickly recap the arc here, we started with this profound economy of nature, just a handful of forces building everything. We saw how those simple laws create ordered shapes, from the quantum rules in a snowflake to the gravitational symmetry of a planet. Then we saw that life isn't a violation of the second law, but a consequence of it, a complex process built on an energy waterfall, probably originating in deep-sea vents.
And all that knowledge culminates in this perspective shift, this realization of our fragility and our unity when we see our world from space.
Can we really appreciate the sheer diversity of life, what Darwin called endless forms most beautiful, without also understanding the simple, elegant forces that birth them? That's the question science forces us to ask, binding those universal laws to our fragile, beautiful home.
For a concise visual tour through the forces that sculpt our world and the universe, see the mini explainer video linked in the description for Forces of Nature.